Hello everyone, my name is Zhibin Guo. I'm an application engineer of Bettersize. This presentation is about understanding the DLS backscattering technology. I'm going to give a brief introduction to it. This talk includes 3 sections: principles, features, and benefits, and summary. The first section is principles. At the beginning of this talk, we need to understand the principle of dynamic light scattering DLS technology. As we know, there are many instruments and methods for particle sizing, and DLS is one of the most popular means for characterizing submicron and nanomaterials. How does DLS work? Briefly speaking, the scattering fluctuations of particles are detected and then converted into correlation function. Then, by using fitting algorithms, the average size based on intensity is calculated. In a conventional DLS analyzer, a coherent laser beam illuminates the uniformly dispersed nanoparticles in the sample cell, which scatter in all directions. The scattering intensity fluctuates over time due to the continuous random walk of particles undergoing Brownian motions. The APD detector determines the number of photons in scattered light at 90 degrees, and the processor computes the sample's autocorrelation function. The diffusion coefficient is then calculated and used to give the hydrodynamic size through the Stokes-Einstein equation. Traditionally, the 90-degree detection is used in DLS analyzers. Now, an advanced optics 173-degree detection is utilized, and this novel design allows intelligent search for the optimal detection position. By moving the lens, the detection point can be set at any position from the center to the edge of the sample cell. This allows the detection of different types and concentrations of samples to be considered. In practice, the optimal detection position and laser intensity are determined intelligently for each specific sample according to its sample concentration, size, and scattering ability. By doing so, the 173-degree detection achieves the highest measurement accuracy. Let's take a close look at it. Scattering volume is the intersection of the incident laser beam and the scatter light intercepted by the detector. When the detection position is in the middle of the sample cell, compared with the 90-degree design, the scattering volume is so big that the detector receives many scattering signals from the particles and increases the sensitivity of the instrument. It has better detection ability for dilute samples, which have smaller sizes and weaker scattering effects. However, the detection is not suitable for samples with extremely high concentrations and very strong scattering effects. Even if the sample is barely detected, the result will deviate from the true value. When the detection position is close to the edge of the sample cell, the laser beam does not need to penetrate the sample, which can effectively minimize the multiple scattering effect of high concentration samples and ensure the accuracy and repeatability of the particle size results in the high concentration range. However, due to its optical design, the scattering volume is so small that it impairs the sensitivity of the instrument, and therefore the instrument is not competent to measure small particles, weakly scattering samples, or very diluted samples under this condition. After understanding the principles, let's move on to the features and benefits. According to our knowledge, there are some drawbacks of the conventional 90-degree optics. For example, the 90-degree optics is not suitable for high concentration range. It's also not suitable for weakly scattering samples. In addition to that, this optics is susceptible to number fluctuations of large particles and also sensitive to the interference of dust and aggregates within the samples. As shown in this figure, when measuring the size standard sample in the original concentration, the 90-degree optics can provide the value close to the certificated value, suggesting its limited concentration range. Well, what are the causes of this great deviation and how do we fix it? There is a common phenomenon in DLS analysis called multiple scattering that we need to know. Single scattering means light is scattered once before being analyzed. Multiple scattering means light scattered from one particle is then scattered by another particle before it reaches the detector, which usually happens in samples with high concentrations, as shown in the right sample cell in this picture. This effect will cause a great deviation in the size measured by the 90-degree DLS analyzer as compared to the true value. As noted in ISO 22412, DLS analysis assumes that only single scatter light is collected. However, at high concentrations, light may be scattered multiple times before being analyzed. Multiple scattering effect increases the fluctuations of the signals. In that case, particles appear to move faster, usually resulting in smaller sizes and broader size distribution. This effect makes the high concentration sample difficult to be measured by 90-degree optics. However, the backscattering technology can minimize the optical path by receiving the light signals at the back angle, and therefore minimize the effect of multiple scattering. In the DLS backscattering technology, for every specific sample, the shorter optical path is achieved, and the optimal detection position is optimized to achieve high-quality results according to its sample concentration, size, and scattering ability. By doing so, the highly concentrated samples can be detected close to the edge of the sample cell, effectively minimizing the multiple scattering effect. As shown in this figure, using the 90-degree detector, the multiple scattering of concentrated size standards reduces the apparent particle size when compared to the true natural. Using the back detector, the results are in much better agreement with the nominal values. Therefore, the measurement of samples across a very wide range of concentrations becomes possible. Another important feature due to the backscattering technology is the increased scattering volume. An increased scattering volume leads to higher sensitivity. For DLS analyzers, two types of sensitivities are usually used. One is absolute sensitivity, which is defined as the absolute scattering intensity of a toluene sample. With a 50 mV solid-state laser, the toluene counter rate is 15 to 20 kilocounter rays per second, abbreviated as KCPS at 90 degrees, whereas the toluene counter rate is more than 300 kcps at 173 degrees. So in terms of the absolute sensitivity, backscattering optics is at least 10 times as sensitive as the 90-degree optics. Another sensitivity is relative sensitivity. It's defined as the minimum measurable concentration for a specific small molecule sample. Here we use lysosome, a very common protein with molecular weight in 14 kilodaltons, to verify the relative sensitivity of the backscatter optics. As we see, when lysosome, such a small molecule sample, is measured across a range of concentrations, the backscatter detection gets much higher quality correlation functions as compared to 90-degree detection. Therefore, in terms of the relative sensitivity, the superior ability of the DLS backscattering technology has been verified. Another benefit of the backscattering technology is higher size upper limit as compared to the conventional DLS analyzers. For large particles, two effects affect the detection accuracy, which are number fluctuations and multiple scattering. On the one hand, the increased scattering volume, which I have mentioned previously, can greatly reduce the number fluctuation of very large particles. On the other hand, the detection position is moving closer to the edge of the sample cell to reduce the multiple scattering effect. Based on the two features, higher size upper limit can be realized. Last but not least, one of the important benefits is better reproducibility. According to mere scattering theory, large, unevenly distributed particles, such as dust and impurities, scatter stronger at forward angles. The backscattering technology can reduce the contribution of the large particles to the scatter signal, resulting in better signal-to-noise ratio and reproducibility. And it reduces the laborious and time-consuming work on sample preparation that traditional 90-degree measurements require. Let's take BSA as example. BSA is a model protein in industrial and scientific research because of its spherical structure and low cost. In this test, it's dissolved in PBS buffer with concentrations of 5 mg per milliliter. When it is dissolved in the solution, it will form some oligomers and aggregates. However, these oligomers usually exist unevenly in the solution, which means they will result in the interference of the results and hence worse reproducibility. As shown in this figure, without sample filtered, the RSD, relative standard deviation of a series of tests, is above 23%. But by using the backscatter detection, the interference of uneven distributed oligomers is minimized, and the RSD is greatly reduced, suggesting better reproducibility. The features and benefits have been walked through. Now let's come to a summary. This talk shows that the DLS backscattering technology has key advantages over the conventional 90-degree analyzers. This technology provides most accurate results, especially for samples on the fringes of the concentration range. By using a backscatter angle, the scattering volume is increased, which is around 10 times as large as the scattering volume of the traditional 90-degree design. Therefore, it brings about 10 times measurement sensitivity, allowing more scattered light signals to be received. The optimal detection position enables the detection near the sample cell wall, so higher size upper limit and better reproducibility are achieved. With these features and benefits, the BeNano series provides consistent and robust data, and is suitable for samples with widest concentration range, and therefore has the widest application range. Alright, this is the end of this talk. I hope you find this video helpful. Please be sure to leave your comments below, and feel free to visit the Bettersize website for more relevant information. See you next time. Bye!